Okay, we want to find the complete factored form of a polynomial with real coefficients that satisfy the given conditions. And we're looking at part A, where we're looking at a function f with degree 2, leading coefficient of 1, and zeros that are 2 plus I and 2 minus I. Okay, so we need a factored form of a polynomial. Essentially, what we're looking at is something in the form f of x equals a, where a might be the leading coefficient, or will be, and then x minus, let's call it x1 being a 0, x minus x2 being another 0, x minus x3 being another 0, dot, 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 until we might get to x minus xn. So some amount of zeros that we're looking at, and n can be the degree of the function we're looking at. We might have some repeats in there, and we can deal with it. Anyways, for this particular problem, we're looking at something with a very small degree, so we're not going to get a bunch of zeros. So we can start with the fact that 2 plus I is 0. What that tells us is that x minus 2 plus I must be a factor. So just like I had above, I have x minus the 0, or x minus the 0 makes the factor. Then x minus 2 plus I, which is a 0, is the factor. Similarly, we have 2 minus I is a 0, gives us x minus 2 minus I is, let's see, is a factor. Keeping in mind that any imaginary 0 is going to come in pairs. So that's why we have 2 plus I and 2 minus I. If you were ever given 2 plus I is a 0 and you're supposed to find the second one, since we know it's a degree 2, we know there has to be another 0. If you're just given 2 plus I, we can assume 2 minus I has to exist because these imaginary zeros come in pairs. So maybe on an exam or something like that, we could give you just 2 plus I and you'd have to find 2 minus I. Anyways, we have f of x equals a being 1, because that's the leading coefficient, so we can leave it out. X minus 2 plus I times x minus 2 minus I. And then we can do some distributing. Get x minus 2 minus I and x minus 2 plus I. That's f of x. And so what you see here is your complete factored form. Now, all we need after that is, it's not asking for it, but we can find ourselves a polynomial in standard form by doing a bunch of foiling. So we can multiply, let's get another color going. We're going to multiply x by everything over here, 2 by everything over here, and then let's get another color again, I against everything here. So we have x times x is x squared, x times negative 2 is negative 2x, x times I is xi or ix. I might put it as ix. Negative 2 times x and negative 2x, negative 2 times negative 2, positive 4, negative 2 times positive 1, negative 2i. I'm sorry about positive I, negative 2i. Negative I times x is negative ix. Negative I times negative 2 is positive 2i. And negative I times positive I is negative I squared. And something interesting is going to happen there. So right off the bat, we can see a few things do cancel. We have ix and negative ix. Those will cancel. We have negative 2i and positive 2i, which are going to cancel. And that'll do it for the canceling so far. So we have x squared, negative 2x and negative 2x can combine to negative 4x. Then we have plus 4, and the negative I squared at the end, I squared is negative 1, and negative 1 is positive 1. So you get plus 1. And finally, we get a standard form of f of x equals x squared minus 4x plus 5. So now we have an equation in standard form and an equation in the factored form in order to satisfy part A.